Yeah. Here the chapter 12. Chapter 12 is perturbation of hydrogen. We already studied for the quantum mechanical calculation of the hydrogen atom, and that is a basic principle in quantum mechanics. But when we apply the magnetic field, then there may have the G-man effect, or by applying electric field, there is a Stark effect. That kind of perturbation is the external parameters like applying magnetic field and applying electric field that applied from the external fields. But how about the internal fields? Internal fields such as the spin-orbit coupling or some kind of interaction between the hyperfine structure. Hyperfine structure means that the interaction between the magnetic moments of the electron spin and nuclear spin. So there's some kind of intrinsic interaction can make another term for the non-degenerated or energy splitting that gives rise to the energy splitting. So that kind of additional interaction can deal with the perturbation theory because the additional interaction is maybe very small comparing to the original Hamiltonian. So, and I will describe what kind of perturbation can be available in the hydrogen atom. When we review the hydrogen energy level, and basically the Hamiltonian of hydrogen of the zeroth order, and it means that unperturbed Hamiltonian is that the kinetic energy minus potential energy it is MKS unit. In the quantum mechanical energy eigenvalue problem can be applied to the here NLM Hamiltonian is applied to the NLM state, and the energy eigenvalue it is unperturbed energy NLM state. Here as we know, and the NLM is that the radial part compose the radial part NL R, and the spherical part LM theta phi. Also there are well-defined solutions in the textbook, and also En0 is ground state non-perturbed energy, that is minus 1 over n square and m over 2 h bar square and E square over 4 pi epsilon 0 and to the scale. Here, and it means that we call it as Rydberg energy, and Rydberg energy, the order of the 13.6 electron volt. Here, this Rydberg energy is the energy basic energy spacing between the quantum level. So here, and when we rewrite the Rydberg energy, by at the 1/2 mc square and 4 pi epsilon 0 h bar c e square to the square, then it is here we can, in this case, we define that it is a fine structure constant. It is a fine structure constant, that is that the 1 over 137. It is a fine structure constant. Basically, this fine structure constant is the measure. It is a dimensionless quantity, and it is a measure of the electromagnetic coupling constant. So, and here E square over 4 pi epsilon 0 h bar c, and it is measure of electromagnetic coupling constant. So in terms of this, and E and 0 can be write down as 1 over n square and 1 half mc square alpha square. So here the unperturbed energy for the 1s state is that n equal to 1, so 1 half mc square alpha square, that is corresponding to the Rydberg energy minus 13.6 electron volt. Here, in this case, just only the Coulomb interaction between the electron and ion, proton in hydrogen. So, but in many cases for the perturbed intrinsic, there are various intrinsic perturbative Hamiltonian, perturbative energy, Hamiltonian. One is that fine structure. Fine structure is that relativistic effect of electron spin, because in the fine structure, this fine structure is order of, for example, when you see that the mc square energy is mc square, and that is corresponding to the 511 kilo electron volt, and also this energy scale is corresponding to the alpha square. In here we can see that it is corresponding to the alpha square. So, and it is order of 10 to the minus 4. So because fine structure constant is order of 1 over 137. So then electronic motion around the nucleus is kind of very can be comparable to the even very small anyway, but cannot be ignored in the speed of light. So, and this fine structure is coming from the relativistic effect of electron by very fast moving of particles. And the other one is the hyperfine interaction, hyperfine structure. Hyperfine structure is the interaction we already studied in the chapter 11. It is coming from the interaction between electron and nuclear magnetic moment. Then also there another one is that the spin-up coupling. Spin-up coupling means that the interaction between the between electron spin s and orbital angular momentum. So we call it as a spin-up coupling, And also the other one is that the Lamb shift. Lamb shift is a result of the quantum electrodynamic effect. So when you see that when we compare with the energy scale, like terms and the energy scale, basically, and the Bohr energy, as we see in the above, and the Bohr energy corresponding to the order of the alpha square mc square. So it is a scaleless alpha square mc square. And the fine structure is the relativistic effect of electron spin at the order of alpha to the 4 mc square. And the Lamb shift case, is order of the alpha to the 5 mc square. And the hyperfine structure is the order of alpha to the 4 mc square, but here there is a term electron mass divided by the proton mass. It is a hyperfine interaction. So this kind of, here we already studied for the hyperfine structure in the chapter 11, actually, frankly speaking, I do not know exactly the Lamb shift, but just only the Lamb shift is a result of the quantum electrodynamic effect. But frankly speaking, I do not know the quantum electrodynamics. Here and in this chapter, I will deal with the fine structure. Fine structure, that is the relativistic effect and the spin-up coupling. So, and this kind of, it is this fine structure, hyperfine structure, spin-up coupling, and Lamb shift is intrinsic perturbation and by the strong interaction. So it makes that energy level splitting, and energy level splitting that makes that degeneracy can break down. So I will find out the fine structure from the fine structure and the spin-up coupling in more detail.